Okay, let's start. So today we will talk about register, latch, flip-flop, different types of latches and flip-flops. In previous lecture, we talk about the latch, D latch, and the D flip-flop. We, this is one D latch and the D flip-flop. The comparison between flip-flop and latch. Both of them can store some temporal data, so they can be used to implement pipeline registers. Particularly, you can use them to implement a accumulator. It can be used to store the intermediate results of the accumulator or adder, and then send the intermediate result back to the input and accumulate with another input. This is the both of them can do that. For the difference, the latch is so-called level sensitive. So when the clock is high, it's transparent. No matter how the input is, the output of the latch just change with the input, even inside that half clock. However, the flip-flop is edge sensitive, so only the rising edge it will change with the input. So you can see at this rising edge, this is 1, so it just keep the 1. Even if the input is changed during this half cycle, the second half of cycle, the output of a D flip-flop will not change. So see, it just keep a 1 like this. And then for this rising edge, this is a 0. This is 0, so it just keep 0. For this rising edge, this is 0, so it just keep the 0. So in this class, we will talk about more types of flip-flop and latches, so that you can implement more flexible functions, more function flexibly. So this is one shift register. And for this register, it's just a sequentially connected D latches. So you can see that they are controlled by one signal, so by one clock. So they controlled by the same clock, and the output of one D latch is the input of another one D latch, and they are sequentially connected. So in this way, you can implement a shift register. So for example, this is a input, and then for this clock, this input will pass to the QA. QA is this latch, and then the QB, and then the QC. It just pass this input one by one. Each cycle, it just shift one D latch. Here is a waveform for 4-bit shift registers. So this is the input. Then the QA just pass this input and V is a 1 clock delay. So this is 1 clock. QA is exactly the same as the input, except it has 1 clock delay. QB has 2 clock delay. Q3 has a 3 clock delay. And Q4 has a 4 clock delay. That's the only difference. We add a clear signal. So only when the clear signal is 0, so the clear bar is a 1, this shift register can do the normal job. When the clear is 1, the output of all beats are just 1. See, these are 1. So the clear signal is somehow a enable signal or a reset signal. And we can even connect the output of the last latch back to the input of the first latch. So in this way, you have a ring here. This is a ring. And we also, this is a so-called ring counter. Another counter means the Johnson counter. The Johnson counter, unlike this ring, it just connect the Q bar of the last latch back to the input of the first latch. I will provide more detail in the following slides. So this is the example of Johnson counter. At the beginning, all the output of these latches are all zeros, and then a 1 move into the first latch, and then another 1. So the first 2 latch provide the output as 1s. First 3, first 4, and then until all the latch have the input as 1. And then because this output is the Q bar here is connected back to the input of the first latch. Here we have a 0. Why this is 0? Because the bar of this one is a 0. And then we use 0 as the new one to do the counting. So what will happen if we have this ring here? So if we have a ring here, we will always have all ones like this. So in this way, it's impossible for us to do the counting anymore. You can only count 8 ones. That's the maximum number you can do. And then you have to do a clear reset. So if we use the run counter, it will be stuck at this stage. But for the Johnson counter, we have the count up process and then count down. So the first half here is the count up. We go up and then we will move down. So this is the difference. Compared to so by only D latch, it's not easy for us to get the Q bar. For the traditional D latch, we only have the Q. The D, the input, is just the output, which we explained in this figure. The input is exactly the same as the output here. So when we have a D, we only have a Q. So it's impossible for us to get a Q bar for the traditional D latch. How can we get a Q bar? So in order to get a Q bar, we need to have a SR latch. The difference between, compared to the traditional D latch, now we have more gates to generate the Q bar here. So it can operated as a simple memory with two stable states as the output when S and R equals to 0. Q1 and Q2 are the output of the SR latch. When Q1 is known as Q, the Q bar is also called the Q2 also called a Q bar. So we have the Q and the Q bar here. So by the SR latch, we can do this. This is not a D latch. This is actually a SR latch. Let's do some calculation. When the S is 0, when the R is 0, we have a NOT gate and another NOT gate here. So this is 1, because these are zeros. So because this is 1, and this is 1, another 1, this gate is a so-called NAND gate. So by the NOT gate, if the first the input is 1, then we have a 1 here. And then this 1 can pass to here. So this is 0. Why? Because 1 and 1 is 1. And the bar of 1 is 0. So if we pass this 0 to here, 1 and 0 is 0. And its bar is 1. So the out here is 1. So this is a so-called stable state. So the function of SR can be summarized as this. So the SR holds can store the data when S and R all equals to 0. So when the S is 1, R is 0. So the output, the Q1 here is 1. When the R is 1 and the S is 0, so the output Q is 0. So we can try this here. So if the S is 1, R is 0. Because this is not gated, we have a 0 here. And we have a 1 here. Because this is a NAND gate, 0 or anything, no matter what value of QR, 0 and anything is still a 0. So it's a bar is 1. So we must have a 1 here. So this is why this is a set operation. For the same thing, if we have the R is a 1 here. If the R is 1, then the R bar is 0. This is also a NAND gate. So we must have a 1 here. And we have a 0 here. This is a reset operation. So we just analysis what's the signal inside and outside of this SR latch for these 3 cases. So if S and R are both 1s, then this is a indeterminate condition. So we will have some raising condition in this SR. The raise condition means we don't know the value. Maybe it's a 1 or maybe it's a 0. It's not a do not care. Please notice that this is not a do not care symbol. This is a raise symbol. It's unpredictable. So by the SR latch, we can generate a Q and a Q bar. This is the benefit, the good point But the bad point is that we have a race condition, which will introduce unpredictable result to your circuit, and that's the disadvantage. Again, to simply implement this SR latch, we do not necessarily require a NOT gate. We can just use NAND gate to do the implementation. And this C here is a enables single signal. So when the C is 1, this NAND gate will be simplified to a NOT gate if this is 1. The result of this output will totally depends on the S. However, if the C is 0, this is NAND gate, so this is 1, this is 1. It just gives you the race condition. So when the C is 1, then it's race condition. This is not good. And this is the truth tables for SR latch. And SR latch with the enable signal with enable C. So you can see that when S is 0, R is 0, we have the last value of the Q. We have a reset here, and when the R is 1, R indicate a reset. That's the, why it's called R. And S is so-called set. This is 1. And we don't have anything here. It's not an X. So if we consider the E here, when E is 0, then we do not care about these two. It just hold. Otherwise, when it's 1 and these are 1s, we have a race condition here. So this is another copy of the SR latches, another copy of the truth table of SR latches. So this truth table, compared to the pure truth table, this truth table provide you the purest value. And the value the SR will generate. So if they are the same, this is so-called hold. If they change, you can set or reset it. So this is the difference. We just break the output into two cycles, the pure cycle and the next cycle. Again, the SR latch is a latch, so it's a level sensitive. If the clock is high, you can, the output just change with the input. The gate will be transparent. In order to implement a T flip-flop, we just add a free-flow circuit to a SR latch here. And then we will analyze what's the function of a T flip-flop. This free-flow circuit is actually a mask. So you can choose Q and Q bar by a mask which controlled by the T. And this is a SR latch. So let's do some analysis. So because this is a flip-flop, so it's triggered by the rising edge. So the T is the input. When T is 1, the Q will change from 0 to 1. When T is 0, it will not change. When T is 1, it will change from 1 to 0. Again, when T is 0, again, this is 1. It will change from 0 to 1. So the T is a kind of a toggle function. When T is 1, the output Q always flipped. And the flipping happens only at the rising edge. But if T is 0, the Q just stay the same. So when T is 0, the output just stay the same. When the T is 1, it's just do the toggle. The function can be summarized by this Boolean equation. You can easily make a T from a D flip-flop. And then we have another copy of flip-flop, which is a JK flip-flop. Unlike the T flip-flop, which is controlled by only one signal, this JK flip-flop is controlled by two signals, which is a J and K. Again, the kernel of this flip-flop is still the D flip-flop, but we just add another piece of circuit here. So when J and K are all zeros, it just hold. When J is 0, K is 1, it do the reset. When J is 1, K is 0, it's just do the set. And when all the both J and K are ones, then it's just to do the toggle. So in this way, we have a hold, toggle, reset, and set function. So you can see that the JK flip-flop is the most powerful flip-flop we have until now. Again, when we break the Q into two cycles, N and N plus, the hold means these two are the same. So the output of two in consecutive cycles are just the same, so it's a hold. If these are all zeros, it's a clear reset. If these are ones, then this is set. Otherwise, just toggle. Toggle means inversion. 0 to 1, 1 to 0. So this is the function of a JK flip-flop. And again, because it's the most powerful flip-flop, the hardware cost is also high compared to previous two. Because here we need a NOT gate, 2 AND gate, and 1 OR gate. Any question?
I have a question about the project.
Yes.
Yeah, so I've been looking at the Shift CNN project and just trying to understand what a reasonable scope as far as our implementation in VHDL is. So, for example, in the paper, I identified that there's a Shift ALU that needs to be made, and then an array of shift registers to store the output from that, and then a separate component that's some multiplexers and an adder tree to sum the result.
Yes.
So is just making like those discrete components and a test bench to prove they are working enough, or do we have to go a step further and add something like the control logic to actually get all of those to?
You have to implement the control logic so that you can do a simple test bench for the network. So basically, the shift and the register, the shift CNN just counts each weight to 2 to n representations. For example, if the weight is 9, apparently this is not a 2 to n. So we quantize it to 8. We just use 8 to approximate this 9. Well, the 8 is 2 to 3. So originally, assume your image or your input is a, let's say 3. So if I use this 3, multiply this 9, I have 27 or something. Now, because I have already done the quantization, I use 3 multiply 8, which is 24. So actually, because this is 2 to n, you don't have to, actually do the multiplication. Instead, you can just shift this 3. 3 is 1, 0, 1, 1, right? Yes, it's a 0, 1, 1. So 1, 1 is a 3. Instead of multiply a 8, you can just do the left shift by 3 bits. Can you tell me what's the value of this binary? So this one indicator is 16. This one indicator 8. Again, 1, 1, 0, 0, 0 is exactly 24. By 3-bit shifting, you finish this so-called multiplication. You have no multiplier. You just do the shift and then the addition. So just implementing a shifter and adder and testing them separately is not good enough. You have to connect them together to do at least something like this. So when you multiply to the first weight, you quantize to 8, you shift it to the left by 3 bits, and then you add it to some intermediate results, and then you do another shift, and then you do the accumulation. I don't think connecting them together makes the project more complicated. But again, you need to show a complete shift and accumulation result.
Okay, that makes sense. I'm just trying to understand what should be the scale of this. So it can range from anything from, a single input value across, a number of channels to a small toy example, kind of like what you had in the deep learning slides, to, something on the scale of an ImageNet inference. So I'm trying to figure out what's the target application for us to do there. Do we show down one value, a small input tensor, or are we trying to replicate something like a larger ImageNet tensor?
Yes,
input?
based on my understanding, the ImageNet this input is 224 multiply 224 multiply 3. This is their inputs. You don't need a, have these many inputs. Maybe you can test a input 3 multiply 3, and then the weight kernel is 2 multiply 2. You can provide me some assumption. This is my assumption, and I use this assumption, these parameters to test my circuits. And of course, these are very large. It's not a practical. Maybe using some small number is good enough. But again, you need to show the shift and addition. You cannot just show the shift and addition separately. Okay.
Okay, that makes sense. I think there's two more things in the paper that I was getting stuck on. One is I was expecting them to describe a shift left, like you described here, but they actually use a shift right, which I guess is just division.
Yes. Because sometimes the weight are just something like this. So if you need to multiply 0.002, then it's a right shift.
I see. And then I guess the last thing is you also previously mentioned maybe doing replicating some of their accuracy results. So is that simply just trying to replicate their results, like quantize a pre-trained model like ResNet or GoogleNet or something, and then rerun our inference like they did and make our own accuracy chart?
Yes. So I didn't expect you can figure out all this stuff at the beginning of the project. You just choose a direction. Again, whether you can do the quantization on a GPU model totally depends on how many persons are there in your group. If you just single person group, you don't have to do that. You just implement the circuit. That's good enough. Again, but if you have a 2-person, the other one can talk to me about that quantization part. And I think we still have 1 month or 2 months to do that. You don't need to worry about that now.
Okay, yeah, thank you. I am in a group of 2, so I was just trying to understand what kind of scope we should.
We can talk about we can talk about these after your first presentation. When you fix your topic, we can talk about more details.
Okay, sounds good. Thank you.
Any question? If no question, we can stop today. Any question, please email me. And you can also ask me at the end of next lecture. Thank you very much.
Thank you.
Thank you.